today, or this week, we're going to finish Multivariate Normal. There's a lot of slides in here. We're not going to use all of them. There's more information than you need. So we'll go through the Multivariate Normal. I'll try to get through it today. And then Wednesday and Friday, we'll talk about how to use this to do inference on mean vectors. Stats 101, you learn how to do t-tests. If you want to test whether one scalar mean equals a particular value, or a two-sample t-test if you want to compare two scalar means. So we're going to learn about how to generalize from t-tests, univariate normal assumptions, and univariate t-statistics to the multivariate case. If you wanted a confidence interval kind of thing, say, for 3 variables or 3 parameters, how can you do that? Or if you want to test whether the mean vector of 3, 5, or whatever p numbers is the same in this comparison group as it is in that comparison group. So there's a multivariate generalization of the one-sample t-test and the two-sample t-test. All right, so we started with what I'm calling topic 4. It's actually our topic 3, but I skipped what was going to be topic 3. So our current topic, multivariate normal, we started this last week. Remember that the PDF, the probability density function for a multivariate normal, has the statistical distance that we've been playing with in its expression. And in particular, it's up in the exponent, e to the minus squared statistical distance between x and mu, scaled by capital sigma. Multivariate normal. Imagine taking the familiar univariate bell-shaped curve and adding dimensions to it. So instead of a bell-shaped curve, you have like this elliptical or bell-shaped surface in the bivariate case. This would be a picture of bivariate normal distribution, multivariate normal, when p is equal to 2. If we had 2 variables. So every individual, we would observe x1 and x2. And as you move x1, x2 pairs around on this on the x1, x2 axis, you see how the probability goes with it. The most probability area under the surface is right under the peak. You can still get unusual values like out in some of the corners, but the probabilities out there are really small. This is a picture when there is no correlation between x1 and x2. Multivariate statistics is interested in preserving correlations between variables. There doesn't have to be correlation. This is what it would look like if there was no correlation. Here's a picture of what happens when you make there be positive correlation. Instead of, what you get with correlation is the peak gets narrower on one direction than in the other. So they kind of move together more so than they do when they're not correlated. I have some R code in topic4.r. So on eCampus, under course content, scripts, topic specific, I have some R code that will go along with some of the notes that we see. We're currently in topic 4. Topic 4.r has some relevant code. So here's topic 4.r. And what I'm going to do is illustrate some of these bivariate or multivariate normal distributions. The library MVT norm has in it some functions we can use to generate random multivariate normal data. So I'm librarying that in, and I'll just run these. These show how to make the picture that's in the slides. no package called MVT norm. Okay, if you get an error like I just did, I tried to library in the package MVT norm. Packages in R are collections of supplementary functionality that sometimes you need but don't come with the base R installation. So I want to use this package, but this computer does not have that package installed yet. So I'm going to go to Packages, Install Packages. I will pick a server that's nearby. And then I need to find MVT norm. Okay, so now let's try again. All right, so now we can use this function. And what I'm going to do is generate a grid of values, x and y. We're going to look at the bivariate normal. So let's let x range from -3 to 3 with 50 points in between. And let's let y range from -3 to 3 with 50 points in between. And then I'm going to use the dmv norm function to compute the PDF. For any distribution in R, like the normal, there is a dnorm function that will evaluate the PDF. There is pnorm, which gives you CDF. There is rnorm, which gives you random draws from a distribution. And there is qnorm, which gives you percentiles. Now we're dealing with MV norm. So there's a D MV norm, there's an R, there's a P, and there's a Q. They all do the same thing. Same thing for Poisson, binomial, all the named distributions. They'll have 4 different functions that you can use for them. Density, CDF, random numbers, and quantiles. I'm evaluating the density. We're going to move x and y over a grid of values and evaluate the density at each one. The outer function I'm using here, you can copy-paste, mimic that code if you need to in our class. I don't need you to know how to do outer all that much. But here's a picture that I get. So you can use the perspective function to make 3-dimensional figures. Here is an example of drawing an ellipse. So you guys are having fun doing that in your homework, right? I posted some code on eCampus that will do it for you. But I wrote a function that if you tell me what mu is, the mean vector, and capital sigma, the covariance matrix, and something that we'll see in a little bit. I'll tell you about this in a little bit. But here's code that does ellipses. We'll make these pictures when we get to them. I haven't gotten there yet. Okay, I'm going back to the notes. This is important. You've seen this. You've done this in your homework. But the idea of points that are a constant distance from a middle point. We're going to be interested in defining where do we go out in order to be an equal statistical distance from the midpoint. And we're going to do that in a particular way to get a region that is a constant statistical distance from where we want to be with a stated probability. And that's going to be like a confidence interval, except now it's a confidence region. It's an ellipse, like you've seen in the homework. Areas of constant statistical distance from mu live on an ellipse or an ellipsoid in higher than 2 dimensions. And this is a restatement of the result that we had in topic 2 about the nature of those points that are a constant statistical distance. If we wanted all the points that are constant statistical distance c squared from the mean vector, we have what we had in the previous topic. The axes of orientation are the eigenvectors of capital sigma, and the half lengths are functions of the eigenvalues of capital sigma. So this is actually nothing new. It's what was in topic 2. It's a region where constant distance, statistical distance from mu. And it is completely determined in terms of eigenvalues and eigenvectors of capital sigma. I'll skip that. Here's some pictures. What I have drawn here is bivariate normal. These are the regions, the points that are equidistant from mu. Mu in this case is 1, 1. x1, the average is 1. x2, the average is 1. The mean vector is right there at 1, 1. The blue curve was drawn in such a way to make, well, obviously it's smaller than the red curve. That's because it contains 50% of the whole distribution, whereas the red one contains 95% of the whole distribution. In practice, we're going to have multivariate data in rows, p columns. Suppose we just had 2 columns, 2 variables. We're going to make a picture like this and call, say, the red surface our 95% confidence region for mu. So I'll be able to say I'm 95% confident that the true value of mu, whatever it is, based on my sample of data, lives inside that red ellipse. That's where we're headed. I have a few pictures of different scenarios. Here's equal variances between x1 and x2. Both have the same variance, and they are positively correlated. If you had bivariate data and you drew a scatter plot and it looked like this, you would have evidence of positive correlation and equal variance. If they were uncorrelated and equal variance, you would have a spherical pattern. There's no bias or preference in either direction. So the two-dimensional or three-dimensional surface is just a completely symmetric, conical-looking thing. Negative correlation, it angles to the opposite direction. Zero correlation, there's no angle to it. Okay. So I'm going to go real quickly through a lot of these slides because I only need you to know a subset of what we're going to see. But with a multivariate normal random vector, if x, capital X, we let that be the random vector, that's p numbers taken simultaneously from an individual or item. When we have normality, things are nice for us statistically. Similarly, in the multivariate case, when we have multivariate normality, there are some nice results that come with it. In particular, when you linearly combine the components of x, like if you have 3 numbers in x, if you do some linear combination of them, that's also normal. All subsets of the x, if you were to partition x like we did in the homework into 2 variables and 3 other ones, those are normal and multivariate normal if there's multiple variables in there. Conditional distributions are also normal. And we have a nice little mathematical result that zero covariance, equivalently zero correlation, means independence, statistical independence. We don't always get to say that. Independence has to do with the probability of one thing being taking a value given the value of the other one. If they're independent, that conditional probability equals the marginal probability. That one variable doesn't care what the other one is doing, and vice versa. And with the normal distribution, we get to say if they're uncorrelated, then they are also independent. But in general, you can't say that. This is not really new for us. I'm just showing you a little bit of notation that writes down what you already know. If X is multivariate normal, it has parameters mu, that's a vector, and capital sigma, that's a matrix. Then consider doing linear combinations, like A transpose X. In your homework, you did this. I said, give me expressions for the mean and the variance of a linear combination of 3 variables. There were 3 different questions that I asked where there were 3 variables. Tell me the mean and the variance of like x1 minus 2 times x2, or x1 minus 3x2 plus 4x3. That's just A transpose X for an appropriate choice of A. For any A, a linear combination of the x's, we already know from topic 2 that the expected value of this, let me write it down on the whiteboard, if X is a random vector with population mean mu, it's a vector, and population covariance matrix sigma. Then consider doing a linear combination of the x's. So A transpose X, that is some constant, the first one in my list of A, A1, A2, dot, 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 AP, times, vector times, x1, x2, xp. So that's A1, x1, plus A2, x2, plus, dot, 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 AP, xp. And what we know from topic 2 is that the expected value of A transpose X is just A transpose expected X. And the variance of A transpose X is A transpose variance of X, A. Same thing as A transpose sigma A. So if you have a random vector X with a mean vector and a covariance matrix, any linear combination, once you figure out what A is, you can just plug and chug with this calculation and figure out means and variances. That's topic 2, and it's showing up here again. What's new on this slide is that we're saying since capital X, since the random vector is multivariate normal, when we do a linear combination, we have the results we just said on the whiteboard from topic 2. Mean is A transpose mu. Covariance or variance is A transpose sigma A. What's new is that the linear combination itself is also normal. When you start with normal, if you do linear combinations, you end up with normal. I'll keep going. Partitioning, we've done this already in topic 2. Same idea here. If I have P variables, capital X is P variables, you could partition it arbitrarily into, say, Q and then P minus Q. Then you have a corresponding P vector that is the mean for the first chunk and a P minus Q vector that's a mean for the second chunk. This should be mu2. That should be a subscript 2. And similarly, the covariance matrix can be chopped up into Q by Q piece for x1 and P minus Q by P minus Q chunk for x2, and whatever is left is in the off diagonals. Notice that these off-diagonal covariance chunks don't have to be square. If we pick Q to be 2 and P minus Q to be 3, for example, then sigma 1, 1 is 2 by 2, sigma 2, 2 is 3 by 3, and so sigma 1, 2 is 2 by 3. What we have now in the multivariate normal case is that if X is multivariate normal, and if we do this, if we partition, then X1, the first of them, is itself multivariate normal. And it has the mean and the covariance that we said up above. So the partitioning thing is not new. That's topic 2. What's new now is we're sticking distributional results on top of it. Conditional distributions are allow you to say, what's the probability of this variable doing something once we know that another variable has done something else. So if I have p variables, for example, I could partition into 2 subsets. I would have 2 separate means now, and I would have a partitioned covariance matrix. With multivariate normal, it turns out, as we saw in the second slide of this topic, that conditional distributions are also normal. And it turns out the mean and the covariance has a specific form. So you may see this again if you take more statistics. I'm not going to test you on it, but at least you've seen it. Multivariate normal, conditional distributions are themselves potentially multivariate normal. The mean and the covariance can be obtained via these results. Okay, multivariate normal. X is multivariate normal, p-dimensional, mean vector mu, covariance matrix capital sigma, with a non-zero determinant, a positive determinant of capital sigma. We have what you are being kind of prompted to conclude in your homework, this result. The statistical distance, if your data are multivariate normal, then statistical distances from mu are distributed chi-square with p degrees of freedom. X is a p vector, random vector, and if you do statistical distance like this, squared statistical distance, it has a known distribution. The value in doing parametric statistics, which is what we are kind of setting ourselves up to do here. Parametric means you postulate, you believe a probability model, multivariate normal. I'm going to measure 5 variables for each item, and I'm going to assume the distribution of those 5 items is multivariate normal, 5-dimensional. When you can make those assumptions, when it's reasonable to make those assumptions, you often wind up with, or you have a better chance of winding up with analytical results that allow you to do statistical inference, which is what we have here. With multivariate normal, this statistic has a known distribution. So that means this holds. The probability that the squared statistical distance is less than or equal to the a particular percentile from the chi-square p is a known quantity. So chi-square p parentheses alpha. That's like a z alpha critical value or a t alpha critical value from Stat 101. When we say chi-square p alpha, what we mean is the number that puts 1 minus alpha, or the number that puts alpha to the right in this distribution. Go to the chi-square p. I'll draw one. Chi-square p. Let's suppose it looks like that. chi-square p 0.05, for example, would be the number such that the area under the curve to the right of it is 0.05. So another way to say that is that's the 95th percentile of the chi-square p. Go find that number, and then you can say the probability statistical distance is less than or equal to that number equals 0.95. If I take alpha to be 0.05, then if I compute distances to this, the probability that my data are inside of this, close enough to mu to be within this threshold, is 1 minus alpha. That expression right there is leading us to confidence regions. When we motivate confidence intervals in Stat 101, we make a statement like this and work our way back from it to intervals. We're going to work our way back from this to regions, like elliptical regions that we interpret like confidence intervals. Okay. Normality and multivariate normality comes up even when you don't assume explicitly that there is a multivariate normal distribution that is guiding your data. You still may run into multivariate normal when dealing with statistics that you compute and when you're trying to do inference. Okay, let me just keep going here. Let's be reminded if we haven't, or be informed if we haven't been familiar with this already, of the concept of a likelihood. We're going to use likelihood multiple times throughout the class. Think about doing statistical inference. Inference is there's a population, there's a parameter in the population that we are interested in. In multivariate statistics, that might be a multivariate mean, like the mean concentration for 5 different elements in the pottery that we're studying. There's a population mean, mu, the true average concentrations for the 5 elements in the pottery we're looking at. But we don't know that value because we're stuck with just a sample that we randomly took of pottery, representative pottery. So we have our sample of, let's say, 100 pots. For each one of them, we have the 5 numbers. If we wanted to estimate mu, the population mean concentrations, we could use our sample average concentrations. Suppose we had 100 rows, 5 columns. We could just average the first row, or average the first column to get the average value of the first variable, average the second column to get the average of the second one, and so on, to get an estimate of mu. But that's only an estimate. In particular, if I sampled 100 pots from our population and measured them, got the 100 by 5 matrix, based on that 100 by 5 matrix, I would compute an X bar, a sample average. Let me draw some things here while I'm talking. So thinking about pottery, suppose P is 5. 5 concentration measurements per pot. So I go do the study. I randomly obtain 100 observations. So pot 1, and here's X1, X2, X5. Here's my 100 by 5 matrix of numbers. From those numbers, I could compute X bar. Call it X bar, sample average, vector of sample averages. This would be X1 bar, the average of the 100 observations of variable 1, X2 bar, X5 bar. So suppose that I did this, 100 pots. My sample averages are 0.1, 0.4, 0.35, 0.02, 0.9, maybe. I saw 5 numbers. Now, if you went and did it again, you sample 100 pots randomly from the whole population, you would replicate this entire picture. You would have your own X bar. If somebody else did it, they'd have their own X bar. So repeatedly sampling from the population, just like we did the one time, 100 pots, you would see variation in your estimate. So when we do have just the 100 pots and one sample average vector, X bar, that's a bona fide estimate of mu. It's a representative estimate of mu, but we know it's not mu, and we know it's subject to variability, because every time you do this, you're going to get slightly different mean vectors. The process of statistical inference is trying to say, here's my estimate, and here's how variable I think that estimate is. That's the value of inference. You get to say, I estimate such and such, and I'm this confident in it. I'm 95% confident in my statement or my decision. In order to do that, in order to get that kind of statement, what we need is the sampling distribution of our statistic, or just the distribution of our statistic. All the words on this slide have been saying X bar is random. It has a distribution. The key to unlocking inference is either knowing analytically or being able to approximate somehow the sampling distribution of your statistic. If we can do that, then we can do confidence intervals, confidence regions, and hypothesis tests. We can do inference. So just to reiterate, to do inference, we need the sampling distribution of X bar. Okay. All right, we need sampling distribution of X bar. There are, okay, so before we get to the end of that story, let me say something more about likelihood. There are multiple ways, there's multiple like paradigms in statistics to do inference. There's not one perfect way or absolutely best way to estimate a parameter and give a confidence level to it. There's different ways. One way that has a lot of good optimality-like characteristics to it is what's called maximum likelihood. So that starts with the concept of a likelihood. Let me just say something about what that is. A likelihood is something you would talk about in the context of observing a random sample. So suppose we're going to take a random sample of n observations from, let's say, the normal distribution, multivariate normal. So x1 through xn, each one of these is a p vector, and they come from some distribution. We're going to say multivariate normal for now. The xi, the individual observations here, because this is what we're calling a random sample, they are all independent of one another. That's what we mean by random sample. And they all come from the same exact distribution, that distribution. So, because of independence, let me write something over here. If x1, x2, xp represent a random sample, then Okay, if they're a random sample, then we can say something about what's the probability, a little bit roughly speaking, what's the probability of seeing those P observations for a given choice of parameter values. Let's think about what is the likelihood, how likely would it be to see my data if the true mean vector, let's just think about the mean vector, is mu. There's two, we'll do mu and sigma, because there's two parameters. Let's think about what's the likelihood of seeing x1 through xp for a given choice of mu sigma. You tell me a value of mu and a value of sigma, and I will evaluate this thing called likelihood. A likelihood, when we have random samples means everybody's independent of each other. So a joint probability of seeing these, this should really be n up here. I'm changing xp to n. Each one of those is a p vector. With independence, the joint probability of seeing all of these x's is just the product of the PDF for each one of them. So I'm going to say product of f of xi. F of xi is like the multivariate normal PDF that we saw. So you tell me what you think mu and sigma are. We can go back to that multivariate normal PDF, evaluate it at xi for each of the i's, product them up. This is, roughly speaking, the probability of observing our data when mu and sigma hold. What I mean by that is we're thinking of this quantity, a likelihood, as a function of what we don't know, the parameters. So this multivariate normal has a mean and a covariance. Those are the collections of parameters. As a function of those things, this is, roughly speaking, the probability of observing the specific data we saw. In terms of doing inference, it's a sensible thing. If I want to estimate mu, for example, it's a sensible thing to work with this and ask what value of mu would make this biggest. If this is a quantification of how likely it would be to see the data that we saw, then we could try changing mu, vary it all over the place, and pick as our estimate of mu the value that makes the likelihood biggest. You would be most likely to observe data like you saw for mu equals something and capital sigma equals something else. In the multivariate normal case, the likelihood as a function of mu and sigma, is product, like we said on the whiteboard. Here's the joint, or here's the PDF, multivariate normal PDF. So you plug in xj for each of your xj, 1 through n, and you evaluate the PDF. How likely is it, what's the PDF of seeing xj if mu is this and capital sigma is that? Evaluate that for all your data points, product it up. And this is, roughly speaking, a joint probability of seeing what we saw when mu and sigma is true. A general inferential way of going about, general way of going about statistical inference is to set this up and then find mu and sigma that maximize it. That is called maximum likelihood estimation. And it turns out that the estimates that you get when you do maximum likelihood have nice properties that makes it nice, I guess, to do statistical inference. I'm going to skip that. I'll skip that. Okay. In the multivariate normal case, if you believe that you have multivariate normal data, you get that n by p matrix of numbers. So it might have been the 100 by 5 numbers of concentrations for the pottery. And we want to estimate the parameters of that distribution. What is the average concentration vector? It turns out, check out the textbook for the math if you're interested, it turns out that the value of mu that maximizes that likelihood is a sensible thing. It is the sample mean, x bar. The maximum likelihood estimator of mu is x bar. And similarly, the maximum likelihood estimator of the covariance matrix is what we called earlier on S sub n. This is a covariance matrix, a sample covariance matrix. What's a little bit unusual about this one is that it divides by n rather than n minus 1. You're used to seeing sample variances defined as like a sum of squared deviations divided by n minus 1. The MLE doesn't divide by n minus 1. So just kind of a minor thing, but the big picture from this right now is that multivariate normal, we know what the maximum likelihood estimators are. So if we're willing to assume that our data are multivariate normal, we're going to have this as an option for doing inference, maximum likelihood estimators. We don't need to know Wishart. Okay, so doing inference, I emphasized on the whiteboard what we need is a sampling distribution. If I want to do inference on mu, population mean, for example, which is what we're going to do when we do the multivariate t-tests. In order to do that, I need to estimate mu, and we just saw that our natural estimate for mu is x bar, sample mean. When we have multivariate normality, we know the sampling distribution of that statistic. It is multivariate normal. That's a result of some of the stuff we saw in the early part of these slides. When you have multivariate normal, if you do a linear combination of the components, you get back normal or multivariate normal. X bar is itself a linear combination. So the sample mean vector is normal itself. It has mean vector equal to the truth, and it has covariance matrix equal to population covariance divided by n. That's analogous to the univariate case where we say x bar has mean mu, a scalar, and variance sigma squared, scalar, divided by n. The variability of a mean is smaller than the population variability. That's why we have 1 over n times sigma. We also know the sampling distribution of S. It's a new distribution that I'm not going to emphasize for us. It's called the Wishart Distribution. It's kind of interesting because it is a probability distribution that applies to matrices. And we have that the two estimates are independent of each other, statistically independent. We're still, just FYI, we're still kind of in the middle of the math background, but we're almost out of it. Okay? As soon as we get out of this chapter, we're going to do inference, actual confidence regions and p-values and stuff, so hang in there. Okay, when we have multivariate normal, then we can do maximum likelihood. Maximum likelihood has a lot of nice properties, but the drawback is you had to specify the distribution at the very beginning. In order to do maximum likelihood, you have to know that PDF. Product up the PDF evaluated at all of the individuals. What if we don't know what the distribution is? Or what if we want it to be multivariate normal, but when we look at the data, they don't look multivariate normal? That's when we have to look at options. One option is that when you have a large sample size, you can often appeal to large sample or asymptotic results, which is what we can do here. If x1 through xn constitute a random sample, so independent and identically distributed, coming from the same distribution, but not necessarily a normal distribution. There's no mention of the population being normal. We just took a random sample from some population that had a mean mu and a covariance matrix capital sigma. But we don't know anything about the actual shape of the population distribution. When you have a large sample size, and large needs to be with respect both to the absolute number and the value of p, how many variables you have. Suppose you had 400 variables and you had 401 samples. 401 sounds like a big number, but relative to the number of parameters that you have to estimate, it's not a big number. So to appeal to large sample asymptotic results, you need a lot of free observations. So what we say in multivariate world is that this large sample result happens when n minus p is big. So the result is, roughly speaking, x bar is normal. We said on the previous slide that if we assume multivariate normality, x bar is normal, period. Now we get to say, even if the population isn't normal, if we have a large sample size, x bar is approximately normal. If you've seen the central limit theorem in Stat 101 or 102, this is a generalization of that. When we do z-tests and stuff, it's like this, except the univariate version. Okay, well, we're out of time. What I want to do with the rest of these slides is, okay, if we have multivariate normality, then we can do this maximum likelihood stuff. So before we go and do maximum likelihood, we want to make sure that normality is a reasonable assumption. Just like in Stats 101, you made QQ plots to check do your data look normal. We're going to do QQ-like things for multivariate normal. And we will talk about finding and dealing with outliers briefly. And we will talk about transforming your data to try to make it be multivariate normal. So suppose you're going to do a t-test univariate case. You do a QQ plot, it doesn't look normal. Maybe you log transform the data and it does look normal. So now you can do t-tests. Same kind of thing here. If my multivariate data don't look multivariate normal, is there maybe a transformation I can do that will make them look multivariate normal? If you've heard of the Box-Cox transform, we'll see that here. There's a multivariate version of it as well. Okay, we're going very quickly. We'll pick up Wednesday, finish this stuff, and we'll do some two-sample or some multivariate t-tests. Okay. Questions right now?